most difficulty with. Okay.
I can't believe they let my sister swear.
So if there are no questions, again, just try to keep it muted unless you have a question, just so we don't pick up a bunch of background sound on the recording. But yeah, we're just going to start with the challenge problems from last Wednesday. So the first one was a dimensional analysis problem. It's dealing with iron 3 perchlorate, right? You find it in the solid form, and you want to know how much of the solid do you want to have just 14 kilograms of pure iron. So that's just going to be a longer dimensional analysis question. And number 2 was my attempt to convert an isotope question into a multiple choice, because again, your exam on Friday is chapters 1 through 3 in multiple choice format. So typically, one like number 2 would be long answer. It was me trying to take a more creative way and making it into, again, a multiple choice question. So for number 1, again, we're being asked how many grams of a solid ionic compound do we need in order to have 14 kilograms of pure iron. Okay, so if we have 14 kilograms, we're first just going to convert that to grams, right? So 1 kilogram is 1,000 grams. That's one of the SI units you guys need to know, right? So you need to know kilo, you need to know centi, milli, micro, and nano, right? Those are all your prefixes. So definitely know your units for that, because you do need to be able to interconvert within the metric system. Okay, so knowing that there's 1,000 grams in a kilogram, you do need to know. Then we can convert to moles of iron, because we know that 1 mole of iron is 55.85 grams. And then we can convert to moles of just iron to our complete ionic solid, right? So there's 1 mole of iron in 1 mole of iron perchlorate, okay? Because that is the molecule we're getting this iron from. 1 mole of that is equal to 354 grams, and then we just convert it to kilograms because the answer choices were in terms of kilograms. And when we do all this math out, we find that in order to get 14 kilograms of iron, we would need to have 88.79 kilograms of that ionic iron perchlorate compound. So that was option B. Okay, number 2 basically asked, is there another isotope present? And if you were like, I didn't know how to do this, well, if there were multiple, I kind of meant for it to be, is there only one other isotope? If there were multiple other isotopes, you wouldn't really be able to solve. But the thing here that I wanted you guys to do is add up the percent abundances of the 3 isotopes that we gave information for. So manganese 53, 55, and 56. And when you add up their percent abundance, they add up to 82.77%. Now remember, when you add the percent abundances of isotopes, they have to add up to 100%, right? Because we want to have our mass of manganese be representative by 100% of the potential isotopes. And so what this number 82.77% indicates is that there's 1 missing isotope, and that its percent abundance would be the difference between that 82.77% and 100%, right? So the remaining percentage, which was 17.23%, is the abundance of some missing isotope. Okay, so that rules out the option of no, and also needs more information because we can solve for this. So kind of at the bottom of the page, the last 4 or 5 lines, that is our more typical equation for average atomic mass. So the first number, 54.938, that is our average atomic mass for manganese as a whole. Okay, and we set that equal to the mass and the percent abundance in terms of a decimal of manganese 53, right? The next 2 numbers are manganese 53, so the mass is 54.065, and its abundance is 42.5%, which in decimal form is 0.425. To that, we add the information from manganese 55, right? So the mass of that is 55.932 times its abundance in decimal form, which is 0.1621, plus our information from manganese 56. So the mass of manganese 56 is 57.555 AMU, and multiply it by its percent abundance, 0.2406. And now at the end, we're going to add our unknown isotope here, right? So plus X, which is the mass of our unknown isotope, multiplied by its abundance, right? We know its abundance is 17.23% because that will get the sum of our abundances to 100. Okay, and basically through this, we just solve for X, and you'd find that X would weigh 52.5 atomic mass units, which was option B. Are there any questions on these two problems? No. Okay. So if there are no questions on that, we can move on to 3 and 4. So number 3, a metal X forms a compound with sulfur with the formula X2S3, right? So this is some ionic solid, okay? And the compound is 29.96% sulfur. What is the molar mass of the metal and identity of the metal? Okay, and so that problem has to do with mass percent and coming up with the molar mass of an unknown compound. And then the one below it, the first note I want to make is this is just an example reaction. I actually don't believe calcium sulfate would be a solid in this case. It just balances out, and I just wanted you guys to use it stoichiometrically. It doesn't necessarily mean it is a true, real reaction. But anyways, this is basically a percent yield problem. I just try to put a little spin on it to get you guys kind of thinking through it a little bit more. And so you're told that you run a reaction with excess calcium hydroxide, and for a little under 4.4 grams of solid is formed, which was 32% less than you were expecting. Based on this, what is the full name and amount of my limiting reactant? Okay. And so in the top part here, it's number 3, right? So we know the formula in number 3 is X2S3, and that by mass, it is 29.96% sulfur, which is, again, our mass percent. So I'm going to input our mass percent formula. So our mass percent of sulfur, which is equal to 29.96%, equals our total mass of sulfur divided by our total mass of the compound. And then the times 100s turn it into a percent. Okay, but looking at the formula of this ionic solid, we know that we have 3 sulfur atoms in this compound. Okay, and so we actually know what the mass of sulfur is. And so we write 0.2996, which is just our 29.96% divided by the 100, right? We're just turning our percentage into a decimal there, is equal to our mass of sulfur, which would be 3, because we have 3 sulfur atoms in this compound, X2S3, times its molar mass, 32.06, over our total mass. So that is equal to, again, our 29.96%, which we just converted to a decimal form. And so from this chemical set equation, we can actually find what the total mass of X2S3 is. When we solve for that, it comes out to 321.03 grams per mole, okay? So when we solve for the total mass of this compound, it is 321 grams per mole. But notice that the total mass of this compound is 2 times the molar mass of X, right? Because there's 2 of them in the formula, plus 3 times our mass of sulfur, right? Because the total mass we solve for still includes the mass of sulfur. And so what we do is we subtract the mass of sulfur from both sides and divide by 2 and find that X is equal to 112.43 grams per mole. Okay, so each atom that X represents is going to weigh 112 grams per mole. When we look at the periodic table, the only element that weighs right about 112.4 is cadmium, Cd. Okay, and we know it's 3 plus just because of the ionic formula, right? Charges balance. If there's 3 sulfurs, they all have a -2 charge. Cadmium needs a +3 charge. Okay, I think the big key to this problem is knowing that once you solve for the total mass of X2S3, it's remembering that you have to subtract out the mass of sulfur and then divide by 2 to find what is the mass of just one molecule of X. Okay, and again, that stands for cadmium. Okay, in number 4, again, they told you that calcium hydroxide is in excess. And so at the end, when they ask you what is the name of the limiting reactant, right? If it's not calcium hydroxide, we know the limiting reactant is Al2SO43, which what is that? That would be aluminum 3 sulfate. Okay, I'm not sure if I actually did write that here, but that is part of the answer. Again, aluminum with a charge of 3 and sulfate. And so kind of the trick behind this is they mentioned in the problem that your yield is 32% less than expected. Okay, so your theoretical yield, right, is 100% of what you expect. That's saying if all your reactants react in the way that they should, you will get 100% of the product you expect. Okay, and so if you have 32% less than you expect, that means that your percent yield is just 32% less than 100%, which is 68% yield. Okay, so I think that's the big tricky part of this problem, is realizing when they say you get 32 less than you expect, that's really in a way telling you that your percent yield is 68%. Okay, and that means that 68% is equal to our experimental yield, how much we actually get at the end of the experiment, divided by our theoretical yield, which again, you find theoretical yield through dimensional analysis, okay? And multiply it by 100, again, to make it a percentage instead of a decimal point. And so what I do here is I divide both sides by 100, so 0.68 is equal to 4.39, so that's how much we were told we collect at the end, right? So we actually experimentally collected 4.39 grams, and we can solve for our theoretical yield, how much we should have gotten in this experiment. And knowing that we only got 68% of what we should have gotten, we can find that we should have obtained 6.456 grams of product, right? Via dimensional analysis, that's how much we should have gotten. And because we know, because it said we had excess calcium hydroxide, and we know aluminum 3 sulfate is limiting, we know that we need to convert to our amount of aluminum sulfate. And so the last step on this page, I take the theoretical amount of product we should have gotten, so 6.456 grams of calcium sulfate, and I, through dimensional analysis, convert this to grams of aluminum sulfate, okay? And so 1 mole of calcium sulfate is 136 grams. It takes 3 moles of calcium sulfate to make 1 mole of aluminum sulfate. And again, we just convert that from moles to grams, and we find that this reaction would have used 5.41 grams of aluminum sulfate to make the 4.39 grams of calcium sulfate. Okay. Are there questions on those two? Okay. Number 3 is traditionally one that they have asked before on long answer questions. So definitely be familiar with that technique. Number 4 is a yield question. It's a little bit unique, in which they typically don't present the information in this way, but they could. So it is a fair question. So again, any questions on how we got to these answers? No? Okay.
No.
Okay, thank you. Okay. Number 5 deals with impure solids, and again, it's just a dimensional analysis problem that, again, is a traditional one that kind of comes up on exams. And then number 6 is our go-to limiting reactant problems. Before getting into these problems, there were 2 edits onto number 6, so I do apologize. The formula for butane was supposed to be C4H10, like they're listed here. Previously, I put C4H8, and it makes your balancing really weird, and also wasn't the formula that I wanted for butane. And so I apologize about that. And then in the second kind of question part under number 6, it said 1.93 moles of ethane. Here it is edited to 1.93 moles of butane. That's what it should have been. So again, I apologize for those mistakes. But again, number 6 is your classic limiting reactant problem. Okay, and so basically, you're told a bunch of information about a solution for number 5, and you're asked how many grams of an impure calcium chloride compound do you need to produce this solution. So we knew the solution was 2.25 liters, right? So we're going to start with that. And we're given the density of the solution, okay? And the density is given as 1.082 grams per milliliter. So when I have 2.25 liters of solution, I know I need to convert to milliliters in order to use my density, right? So 1 liter is 1,000 milliliters, and now we can use the density that was given the problem to convert to basically grams of solution. Okay, so 1.082 grams of solution per 1 milliliter. Now, this is about halfway through the dimensional analysis. We don't actually care about how many grams of solution we have. We care about how many grams of calcium chloride and impure calcium chloride we have. And so the next conversion factor I use is to convert from grams of solution to grams of just calcium chloride, right? And so you're told in the problem that the solution is 25% calcium chloride by mass. And so that tells you that per 100 grams of solution, you have 25 grams of calcium chloride, right? So that's how I got that kind of third conversion factors in this dimensional analysis. Now again, the problem is asking how many grams of impure calcium chloride do you need to produce this solution, and that this impure mass of calcium chloride is only 92% calcium chloride by mass, which means, and this is for our last conversion factor, that we use 92 grams of calcium chloride per 100 grams of this impure calcium chloride solid or mass, right? And so when we do all this dimensional analysis and we look at all of our units, the end number, which comes out to about 660, is how many it's grams of impure calcium chloride you have to make this solution, and so the answer is 660. And again, kind of clarification, look at the units to make sure, right, your units cancel out. So at first, we use all information regarding the solution itself. Then we use the second to last conversion factor allows us to go from mass of solution to mass of calcium chloride. Then the last conversion factor is mass of calcium chloride to mass of our impure calcium chloride. Okay, so units can kind of help you there. Number 6, so this is your equation written out. So right, we have liquid butane. When you write this equation out, all of your all of your states of matter should have been in there. Your equation's technically wrong without all your states of matter. So it should have been butane in the liquid plus 3 diatomic nitrogens. So remember, nitrogen gas is diatomic, and again, it's in the gaseous state. This goes to 4 cyanic acids. And again, remember, acids are always in your aqueous state. So that's how you know that HCN should be in the aqueous state. And then we have 2 gaseous ammonia particles as the other product. And again, remember it's ammonia, NH3, not ammonium, NH4+. Okay. So after writing the balanced chemical equation, our first step was to find what the limiting reactant is and how much cyanic acid can we produce. And so personally, I always take how much of each reactant I have and I convert all of them to amounts of this cyanic acid, right? Because not only will we answer what is our limiting reactant, but we'll also answer our second question, how much product can we form? So from, and this was given, 1.93 moles of butane, right? 1 mole of butane can form 4 moles of cyanic acid. That's from our balanced chemical equation, looking at our coefficients. And 1 mole of that is about 27 grams. And we find that based on our butane, we can make about 309 grams of cyanic acid. Now, from 1.34 moles of nitrogen gas, right, it's 3 moles of that to make 4 moles of cyanic acid. And again, just converting it to grams, we find that we can only make 48.29 grams of cyanic acid based on our nitrogen gas. And so because we can make fewer product based on our nitrogen gas, that is our limiting reactant. Okay, so N2 is limiting, and 48.3 grams HCN is how much we could produce. Now, the next step asked how much excess reactant do we have? So whenever you're solving for excess reactant, you're going to take how much product you can form and almost go backwards. Okay, so how much product could we form? We could form 48.3 grams of cyanic acid. Okay, we're going to convert this to moles using its molar mass, and then convert from moles of cyanic acid to moles of butane, which again is our non-limiting reactant, right? It's not the limiting reactant. And what we find, I actually converted all the way to grams, but I actually asked for it in terms of moles, and so I wrote both. When you do this dimensional analysis, you find that it comes out to 0.447 moles. Now realize that this amount that you come out with, this product, is in terms of how much you used up during the reaction. Okay, so I don't have 0.447 moles of excess butane. That's how much I used. And so I started with 1.93 moles of butane. I used 0.447 moles, and so I have an excess of 1.48 moles of butane. Okay. And lastly, you're told that you have 72% yield. How much did you experimentally get? Well, in step 1, we found that we theoretically should produce 48.3 grams of cyanic acid. So we put that in the denominator. We're solving for X, which is how much we experimentally would have acquired after this reaction, and we find that we would have been able to collect 34.8 grams of cyanic acid. And again, we do this based on the fact that there's 72% yield. Are there questions on any of the challenge problems?
I have a question on number 5 that's on the screen right now.
Yep.
Can you just say again how you got the 25 over 100 gram step?
Yep. So I'm just going to go back one slide to the question. And so right at the second line, or kind of the first line going into the second, it says to make 2.25 liters of a 25% calcium chloride solution by mass. Okay. And so if you look at the units up to that point, everything would have canceled out, and except for we really have grams of solution, right? But we don't care about how many grams of solution we have. We care about grams of just the calcium chloride. And so because it's 25% calcium chloride by mass, the solution is, we can use the conversion factor of 25 grams of calcium chloride is 100 grams of solution. If you wanted to put 0.25 grams of calcium chloride is 1 gram of solution, that's also okay. Really, that conversion factor there just needs to represent kind of a 25% ratio, if that makes sense.
Okay, thank you.
Yep. Any other questions?
For how did you get 1.082 for the same problem for 1.082 grams of solution per 1 milliliter?
That I think was given at the very end. So kind of after the question, it says assume the density of the 25% solution is 1.082.
Okay, got it. Thank you.
Yep. Any other questions? And again, number 5 is a pretty typical one to see on an exam. It might not be a solution like this, but they do, they very often, especially long answer exams, I know yours is multiple choice, but they'll ask kind of using, this is kind of the an idea of an impure compound. Those you often see, and before your next long answer, we'll do more practice with them. Okay, because it kind of uses percent composition as a conversion factor very frequently.
I have a quick question about sig figs for question 5.
Yep.
So since it's 2.25 liters of solution, wouldn't it be 3 sig figs? So wouldn't it be 662 grams? Or how'd you round down to 660 grams?
So yeah, so I actually had the debate with myself as well, which is why I wrote 662 originally and then drew the arrow to 660. What I would say, and they would be more clear on an exam, probably what I would say, and I'm going to again go back to the question, is they say it's 92% calcium chloride by mass, and that's the impure solid. And then they also say that it's 25% calcium chloride solution. I would probably ask myself, that's probably something they measured, and those themselves would probably play a role into the sig figs. And so I'd say that I answered it to 2 sig figs because of those two numbers. Those are both only 2 sig figs. But again, I think that's a little bit trickier than they would mean to be on an exam. On an exam, I'd probably, if they said 2.25 liters of solution, I have a feeling they would say 92.0% calcium chloride by mass, and that the solution is 25.0% calcium chloride by mass. Because yeah, that was a little trickier than I meant for it to be in terms of sig figs.
Okay, cool. Would that show up on a multiple choice question? Like one of the options being 662 and another option being 660? Like, would it be that close if it was?
I would highly, highly doubt it. Unless they're asking you very specifically about number of sig figs, they typically don't do little tricks like that. And so the trick, especially for a problem like this, there's a lot of spots that you can make a mistake. And so they're probably more trying to get you on one of those mistakes rather than do you know it's 2 versus 3 sig figs. Again, multiple choice questions, it's typically did you get the math portion of it right rather than are your sig figs correct. That being said, definitely check on the exam. They could do 662 and 660, but I doubt it.
Okay, cool. Thank you so much.
Yeah, no problem. Any other questions on these challenge problems? Okay. If questions do arise, again, a lot of tonight is a review. I think all of the challenge problems I made tonight are multiple choice problems, so you can kind of see it in terms of that. But we are just for probably about 5 minutes or so, max 10, just going to go over a few things from chapter 4. We will pick this stuff up again on, and I wrote molex instead of moles, under molality. But we'll do this more on Monday, a week from today. But again, we're just going to do 5 or so minutes of new material for chapter 4, which is not on your exam Friday, before going to review stuff. So something I want to just point out is the difference between molarity and molality. And so molality, traditionally, they actually don't teach until next semester because you don't really use it much. But because they taught it, we'll talk about it, and I'll kind of teach you next week how to interconvert between them. But it's more important just to distinguish between them right now. So molarity is how many moles of solute you have per liter of solution. Okay, and so solute, again, is typically a solid that you dissolve in what we call a solvent, which is typically a liquid, right? So the classic example is if you pour sugar or table salt, NaCl, into water, right? Your solute would be your sugar or your salt, and your solvent would be your water, and then together they are your solution. Okay, so molarity is moles of solute per liter of solution. Okay, and we use this actually a lot. Both this semester and next semester, we will use molarity all the time. And it allows us to convert between volume and moles. And remember that moles is our base unit of comparison, right? If we're ever converting from one compound to another, we always need to convert it to moles because, again, it just allows us to interconvert. And so one thing that I wrote is just 18 molar H2SO4. Okay, so the big M like that means molar, which is standing for molarity. And what that means is if you have 1 liter of 18 molar H2SO4, it means that it contains 18 moles of sulfuric acid in that 1 liter. Okay, but just because it says 18 molar doesn't necessarily mean that it's only 1 liter. Okay, it also could be 18 molar and be a 2-liter solution, in which case it would just have 36 moles of sulfuric acid inside of it. Okay. And then molality, again, sorry for the typo, it's moles of solute per kilogram of solvent. Okay, so just the big things to kind of underline here is that your numerator here will still be moles of solute, but your denominator, what you're dividing it by, first off, it's in terms of kilograms, not in terms of volume, right? So molarity is liters, which is a measure of volume. Kilograms is a measure of mass. So that's what we're using in molality. And also it's of solvent. Okay, so it's actually of what we typically see as the liquid portion, not the whole solution itself. Again, in terms of the math regarding these, we will focus on those more next week. But we brought up molarity, and this we typically see in the terms of dilution, which is actually a pretty big part of this chapter 4. Okay, so what is a dilution? Okay, so it's a process where you add water to something that's more concentrated, which we'll call the stock, to decrease its concentration. Okay, and how you kind of think of this is, again, molarity is moles of solute per liter of solution. So if you're adding water, okay, that means you're really increasing the volume of that solution, right? You're increasing the denominator of this molarity equation. But if you're adding water, you're not increasing the moles of solute. And so that kind of explains why, if you're increasing the volume but keeping the moles of solute the same, that's why your concentration is going to decrease, okay? And when we do dilution problems, you will typically use this equation. Now, there's 2 different variations of it. They mean the exact same thing. Okay, so C1V1 equals C2V2, or you might write it as M1V1 equals M2V2. Okay, and the reason you kind of see it both ways is C or M stand for concentration or molarity, right? And so molarity, that big M, is typically how we see concentration reported, right, in moles per liter. And so if you have a stock solution, which is your concentrated solution, that's going to be your C1 or M1, right? And the more dilute version is going to be your C2 or M2, okay? And V in the above equation stands for volume. And it's typically in liters or milliliters. One thing to note, okay, even though molarity, your concentration unit, is in terms of moles per liter, you can plug in liters or milliliters in this equation for your volume, right? The important part is that you stay consistent on both sides, okay? So if you plug in for V1 50 milliliters and you're solving for V2, whatever answer, numerical answer you get for V2, you have to remember that that is going to be in terms of milliliters, okay? So you can use liters, you can use milliliters in this equation as long as you stay consistent from one side of the equation to the other, okay? And your concentration will pretty much always be in terms of moles per liter, which is molar, okay? And again, kind of talking about solubility. So the solute, right, we add that to a solvent, and when that happens, they often dissolve and ionize. Okay, now ionizing just means something splits into its ions, right? So NaCl would split into Na plus and Cl minus, right? An anion and a cation. Okay, and so strong electrolytes are compounds that ionize completely, right? So if you have 10 molecules of NaCl, they're going to split into 10 Na plus ions and 10 Cl minus ions. Some molecules called weak electrolytes only partially ionize, which means if there are 10 molecules of a weak electrolyte, maybe 4 of them will become their respective ions, and 6 of them will stay together as a compound, right? And then there's others like glucose that do not ionize at all. These are called non-electrolytes. And all it means is that when it's put into something, a solvent like water, it doesn't split into ions, it just dissolves, right? And something in terms of like glucose, for example, it's not made of ions, and so that's why it doesn't ionize, right? It just stays as a covalent compound. And so we're going to see this in chapter 4 as precipitation reactions, which is just the last new topic we're going to talk about. All the math we'll deal with next week, but just to talk about what it is. So in this type of reaction, we form what we call a precipitate from ions. Okay, and so I kind of describe what the format of this is. And so on the reactant side of this chemical equation, you're going to see 2 or more ionic compounds, and they're all going to be in the aqueous state, right? And then on the product side, we're going to see probably some ionic compounds in an aqueous state, but one ionic compound made of 2 ions will form something in the solid state, which is what we call the precipitate, okay? Now, to figure out which product is going to form this solid compound, we use a solubility table, which is in the upper right-hand corner, right? This is a screenshot of your solubility table that's on your equation sheet that you have for exams. The important part is that you know how to read it, okay? And so to use it, basically anything that is a white square is what is soluble, right? That means it's going to be in the aqueous state if you put it in water, for example. So in the upper left-hand corner, for example, we have as our anion nitrate, NO3 minus, and next to it, it says group 1 cations and NH4 plus. That means if we have, for example, ammonia nitrate, which is NH4 plus, NO3 minus, if that is our ionic compound, because it's in a white square, it is soluble, which means it will not form a solid, okay? It's dissolvable. Because the key to precipitation reactions is actually that we don't really care what is soluble, we only care what is not soluble, which on a solubility table is indicated by the gray squares or formulas in gray, or if you look at it in color, it's in green, right? And so anything that's in gray will be insoluble, which means on the product side of a precipitation reaction, it would form the solid, okay? And so if you have magnesium hydroxide on your product side, for example, you can see that's in gray, that would form your solid, okay? Okay, now we're going to do the activity. If anybody has questions on what I just went over, I know I kind of went through pretty quickly, but feel free to ask it. Just in the chat to sign in, please use your net ID. So that should be a combination of 3 letters followed by 5 numbers. And we're going to take about 4 or 5 minutes. Please try to write a difficult problem from chapters 1, 2, or 3. Okay, so any of those chapters, or even a portion of the problem. Like you don't have to write a whole problem on your own. It might be balance this reaction, or I don't know, name this compound. But try to take some time to do this, and try to make them difficult, because I am going to use these and make them into practice problem for Wednesday night to review for your exam. And also, I've found that I've honestly, from SI, from making problems myself, I've actually learned the material much, much better. So if you ever get your depth of understanding for exam content to the level where you can actually ask difficult, almost exam level difficulty questions, that means you've probably mastered the topic or become close to mastering the topic. So again, take some time, Don't worry if there are slight issues with it. I'm going to tweak some of these if there's portions that don't work out in them. But again, they're only going to be given back to you guys so that you guys have plenty of practice yourselves for your exam on Friday. They don't need to be multiple choice questions. I would take multiple choice or short answer. And before I just let you work on this for a couple minutes, if anybody is watching this as a recorded video late and you want to do this to practice the content, feel free to send me the problem you make via my email, and I will include it in the review sheet from these problems. Okay, so again, take just, we'll probably say 4 minutes, and then we'll continue on with review. The review will be on limiting reactant problems, combustion reactions, and molecular empirical formula questions, since those seem to be the ones people tend to have most difficulty with. Okay, so just some time to work on it. Also, if you find any hard homework problems, any problems you've struggled on, those are also welcome to make this practice sheet.
Where did you want the problems?
If you can just send it into the chat, that'd be awesome. If for some reason you can't, if you want to email them to me, that'd also be okay. But yeah, I was kind of thinking the chat, but if for some reason you can't, that's okay.
Yeah, I was just wondering.
Okay.
Hey, I just have one random question.
Yeah, go ahead.
So I was a bit confused. Is it like whenever I'm trying to find out if something is solid or aqueous or whatever, should I just use that chart in the equation sheet?
Yes, so definitely use this chart. Really, without that chart, you can't be expected to know what will be a solid and what will be aqueous.
Okay.
And occasionally when you're doing problems, maybe in your book or on your homework, you might see something that forms a solid that is not in that chart that they give you. Maybe they just don't list that exception or something. On an exam, any solid that forms from a precipitation reaction will be on that chart. So as long as you can use that chart, know how to use it, and realize that anything that's in gray is going to form a solid, in terms of identifying the solid, that's really all you need to be able to do.
Okay, thank you.
Yeah.
Also, one other thing, how many questions is the multiple choice exam normally?
Yeah, so good question. Most of the years I've taught this, we had multiple choice and short answer on the same day in an hour and a half. And so based on how much time you guys get and stuff, it might be slightly different, but I would probably predict between 15 and 22 questions. This one might be a few longer. It might be a bit on the longer side because some of the questions you will pretty much be able to look at and know the answer within about 5 to 10 seconds. And for examples of that, look at any of the challenge problem multiple choice ones I've given, especially from chapter 1. So for example, what is the classification of CO2? Is it an element, a compound, a heterogeneous mixture, or a homogeneous mixture? Okay, CO2 we know is a compound. So something like that would take you very little time. And so it might be 22, 23 questions, but it wouldn't be longer than that.
Thank you.
Yeah. Okay, so keep sending in those questions. There'll be more time. I've looked at some of them. They're so 21 questions. So awesome. So the exam Friday should be 21 questions. I've looked at some of these questions already. Thank you guys. They're actually really, really good questions. They'll be really great to help you guys review. So again, I'll kind of edit those over the next couple of days, and that'll be our focus for Wednesday. It'll just be chapters 1 through 3 review. So I'll kind of go through all the big topics, try to jog your memory on some of the harder details, and then just practice. Okay, so I just wanted to go through limiting reactant problems, empirical molecular formula questions, and then combustion reactions. Because when I asked you guys what are the hardest topics from chapter 3, those for the most parts were the ones that I saw reoccurring every time. Okay, so these are just kind of notes that you guys already have. Just a reminder of what a limiting reactant is. So whenever the professors give you how much of multiple reactants you have, so maybe 10 grams of reactant A, 20 grams of reactant B, whenever they give you the starting amount of multiple reactants, you are going to have a limiting reactant problem. And basically why you have this is the amount of product you can form is going to be limited by how much reactant you have, right? So kind of my easy example at the bottom is if you have 1 jar of peanut butter, 1 jar of jelly, and 2 pieces of bread, how many PB&Js can you make? Well, based on the peanut butter and jelly, you might be able to make 30, but because you only have 2 pieces of bread, that is your limiting reactant. That is going to prevent you from making more products than the others would allow. Okay, and so what this is kind of going through the typical questions and then my verbal description of kind of how to solve it. But what I'm going to do after this is I'm going to bring up a problem that we've already done in a past SI, or one of them I did with some students during office hours or something, and I'm kind of going to highlight what each step is referring to. And so you'll see in a minute. And so the typical limiting reactant questions is which reactant is limiting and how much of a product can be formed. And so to answer these 2 questions, you should convert all of the reactants to the amount of product in question, right? So one of the challenge problems we went over today, it asked how much cyanic acid can we make? So I took all the amount of each reactant we had and I converted it to how much of cyanic acid I had. And I knew that the reactant that forms the least amount of product is my limiting reactant, okay? And again, I'll show an example of that in a minute. The other question that's extremely typical to be asked is how much excess reactant is there, okay? And so to do this, you take the amount of product that was formed, right? That we found that from the first part, and we're gonna convert it to the amount of non-limiting reactant, right? We're going to do dimensional analysis and convert it to the amount of our non-limiting reactant, okay? The product of this dimensional analysis is how much we used, okay? And I think it should say used of each reactant. So I apologize. That's how much of the reactant we used up. Okay, and so to find excess, we're going to subtract the amount that we used from the amount we started with. Okay, and so the example we're going to use is this equation. And again, this is one we've done before, right? So up top, this is a combustion reaction with a hydrocarbon. So C5H12 reacts with oxygen to form CO2 and water. Okay, and you're told we have 32 grams of hydrocarbon, we have 126.5 grams of oxygen. They want to know what the limiting reactant is, how much CO2 we can make, and how much excess reactant there is. Okay, so right off the bat, I would kind of look down and see, okay, how much, like what product are they asking me for? And they want to know how much CO2 I can form. And so I know my first step should be, and this is the part in red here, I should convert how much reactant I have to grams of CO2, because they eventually ask me for that. Okay, and so I start with 32 grams of my hydrocarbon, and I convert that to moles of hydrocarbon. From my balanced chemical equation, it takes 1 moles of HC, which just means hydrocarbon, to make 5 moles of CO2. And basically I find that from 32 grams of my hydrocarbon, I can form 97.6 grams of carbon dioxide. Okay, now I'm going to do the same exact thing for my other reactant. So 126.5 grams of oxygen. I go through and I find through dimensional analysis that I could form 108.7 grams of CO2. Okay, and kind of below this box, you can see my first line below it. It says that C5H12 is limiting and that 97.6 grams carbon dioxide can be formed. Okay, so that's kind of the first step that I outlined on 2 slides ago, like verbally, right? Whenever you're given the amount of reactant for multiple reactants, you're going to convert to the product in question, right? So they asked how much CO2 can we make? And so I converted my amount of both reactants to grams of CO2. That not only helps me identify which reactant is limiting, but it also helps me answer how much product I can form, which remember is the smaller amount. So no, I can't make 108 grams. I can only make the 97.6 grams. Okay. Now the second part of the question asked me how much excess I have. So whenever you're asked to find excess, you're going to start with the amount of product you could form, right? So in part 1, we found that we could make 97.6 grams of CO2. We're going to take this and we're going to convert backwards to our non-limiting reactant, okay? So because our hydrocarbon is limiting, that means that we are going to convert this to grams of oxygen, okay, O2, because that is our non-limiting reactant. And when we do this dimensional analysis, right, so 97 grams of CO2, 1 mole of that is 44 grams. From our balanced chemical equation, we know that it takes 8 moles of oxygen to make 5 moles of CO2, and that 1 mole of oxygen weighs 32 grams. And this helps us find that we used up 113.5 grams. Again, remember that the product of this dimensional analysis is how much you used up, okay? And so in order to solve for the excess, we take the grams of oxygen we started with, 126.5, and we subtract out the amount that we used up, 113.5, to get 13 grams of excess oxygen. Okay, and then the last one was a percent yield question, but are there any questions on that? And if you want me to go through the percent yield, I can try to remember it. Actually, I think I do remember what the question was. Are there any questions on this, though, limiting reactant? There also will be practice tonight through the challenge problems, but no? Okay, the other really common thing that I saw people ask about is empirical-molecular formula questions. Now again, this was on a previous SI. This is me trying to verbally describe kind of how to go about this, but same thing as the last problem we just did. We're gonna break this down into smaller chunks so you can kind of see what steps are associated with each of these. So your first step is to get grams of all your compounds, right? And so often you'll be given atoms in terms of mass percent. And so we're just going to assume we have 100 grams of compound, allowing us to drop the percent and just write grams. So the example of this is if you said that there's a compound that's 60% hydrogen and 40% carbon. If we assume that there's 100 grams of compound, all that means is that there's 60 grams of hydrogen from that compound and 40 grams of carbon. Okay, so again, convert first to grams. Once you have grams of each of your atoms, you're going to convert them to moles, right? So moles of each element, okay? Once you have moles of each element, you're going to divide them all by the least number of moles to give you a whole number or a ratio between them. And then if needed, you're going to multiply this ratio by some coefficient, making them whole number ratios. Okay, so this step is only needed if you're dealing with decimals. Okay, and then the last step, which is only needed to do if you are asked for a molecular formula, is you're going to divide the molar mass of your compound by the molar mass of your empirical formula, and the quotient of that you're going to multiply all the subscripts by in your empirical formula to find your molecular formula. Again, we are going to break this down. Okay, so again, I think this is an example I gave a couple SIs ago. And so you're told that an unknown compound has 30.16 grams carbon, 5.06 grams hydrogen, and 26.78 grams of oxygen. You're also told that it has a molar mass of about 222 grams per mole, and you're asked for the molecular formula. Okay, so in red right now is our first step, okay? So we kind of first need every atom in terms of how many grams we have of each of them, which was actually given to us, right? So we were told we had about 30 grams of carbon, 5 grams of hydrogen, and 26.78 grams of oxygen. So I first wrote that. Once we have everything in terms of grams, we have to convert all of these to moles. And so that's what I'm showing in this box here, right? 30.16 grams of carbon is really 2.51 moles of carbon. 5 grams of hydrogen is about 5 moles of hydrogen, and 26.78 grams of oxygen is really 1.78 moles of oxygen, right? So first get each element in terms of grams, then get them each in terms of moles, okay? The step after that is to divide all of them by the least number of moles, right? So we have about 2.5 moles of carbon, 5 moles of hydrogen, and only 1.67 moles of oxygen. So 1.67 is the smallest number of moles out of those three. And so we're going to divide all of our numbers by 1.67, right? So 2.5 moles of carbon divided by 1.7 gives us about 1.5. 5 moles of hydrogen divided by 1.67 gives us 3. And then 1.67 divided by itself gives us 1. Okay, now those numbers are our ratio between carbon, hydrogen, and oxygen. But this step we're taking right here is that second to last step I verbally described.
He does
right?
practice problems, and he explains all the topics on the worksheets. And he'll go through it step by step. He's actually really good, bro. And look, you go to, let me show you how to go to it.
I'm confused. I'm going to keep going through this one. If you want me to go over something at the end, I'm happy to do so.
Sick. Oh.
You can just send the question.
On the left side, SI information.
Oh.
And you click on Ryan's session. You can go to his sessions are Tuesday, Thursday, or you just go to his videos. He has reviews.
Okay. Sorry, I just picked up some people, and so I just muted people temporarily just to get through this so that it wasn't getting picked up. But if you have questions, just let me know, and I'll unmute you guys to hear. I'm just going to get through this problem. So from this ratio, from the last step, we know that we have 1.5 carbons for each 3 hydrogens and for 1 oxygen. But we can't, although that is the ratio between them, in an empirical formula, we cannot have decimals. So we have to multiply these subscripts by some number that gets them to a whole number ratio. And so 1.5 times 2 will get it to 3. So I'm going to multiply all those subscripts by 2, and that gives me my empirical formula, C3H6O2. Okay? And you can see I also wrote the molar mass of that. If you calculated it for the empirical formula, it would come out to 74 or so. Okay? So just the last step is they asked for the molecular formula, not our empirical formula. And so to make this jump, okay, you're going to take the total molar mass of the compound, which was given to us. It was 222. They will give you that, okay? And we're going to divide it by the molar mass of our empirical formula, right? So our empirical formula is C3H6O2. That molar mass would be about 74. And so we're going to take the overall molar mass, 222, divide it by the molar mass of our empirical formula, 74, and that'll get us the quotient of 3. Now to go from the empirical formula to the molecular formula, you take that quotient you just solved for, which in this case, again, is 3, and you multiply all the subscripts in your empirical formula by it. Okay, so instead of C3, it's going to be C9. Instead of H6, it's now H18, and instead of O2, it is going to be O6. Okay, and that's how you make the jump from empirical to molecular formula. Okay, I will see if it's quieter now. Okay, again, if any of you has questions, I think you should be able to just unmute and ask. So does anybody have any questions up to this point?
Could you repeat how you got the 222.23 back there?
Yep, it was given in the problem. So I'll go back for a second. So the very last sentence, if the molar mass of the unknown compound is 222.23, what is the molecular? If they ever want you to solve for the molecular formula from an empirical formula, like all these problems have you do, they have to give you that molar mass of the whole compound. So they have to give you that 222 number.
Thank you.
Yeah, no problem. Okay, any other questions before combustion analysis? And combustion analysis is very similar because they will also have you derive an empirical formula or molecular. But questions before we begin it? And this is the last topic for tonight as well. Okay, if there are no questions, so I'm just going to talk about what a combustion analysis is. So the typical problem is you will be given a compound made of carbon, hydrogen, and oxygen. Typically, you are not told how much of each you have, right? It's an unknown compound. And it's going to react with oxygen in the gaseous state, so it's going to be O2, diatomic gas, and that's going to form, on the product side, both CO2 gas and water. Okay, and again, in the typical problem, they are going to give you the mass of carbon dioxide that you form, water that you form, and how much compound you started with. Okay, all of those will be in terms of grams, typically. Okay, so what's the general process for these types of questions? So when you look at the chemical equation, you'll notice that carbon is only in the balanced equation in 2 spots. It's in our unknown CHO compound, okay, and it's in CO2, carbon dioxide. And so from knowing this, if you take the mass of CO2 that you produce, you can actually find the mass of carbon, which directly comes from the unknown compound. So from the mass of CO2, you can find how many grams of carbon are in our unknown compound. Now, using the mass of water formed, we can do the same thing for hydrogen, right? So using water, we will find the mass of hydrogen in the unknown compound. Now, lastly, we need to find the mass of oxygen, which we find by subtracting the mass of carbon and hydrogen from the overall mass of the compound, which again is a piece of information we're often given in the problem, okay? And then once we have the mass of oxygen, carbon, and hydrogen, we kind of solve it in a very similar way to our empirical formula questions, okay? Before going on to a practice problem, which I did in office hours with some people, I just want to talk about some variations you might see. One thing to note, although in a combustion reaction, again, we have a compound with carbon, hydrogen, and oxygen, and this reacts with oxygen to produce CO2 and water. That's typically how we see it. But instead of a compound with C, H, and O, sometimes we will see compounds with just C and H, so they might just be a hydrocarbon. And you might also see a question like the one we are about to do, which is why I chose this. Okay, so complicated chemical reactions occur at hot springs on the ocean floor. One compound obtained from such a hot spring consists of magnesium, silicon, hydrogen, and oxygen, right? So we have 4 elements in this unknown compound, okay? From a 0.301 gram sample, right? So a 0.3 gram sample of this unknown compound, the magnesium is recovered as 0.104 grams magnesium oxide. Hydrogen is recovered as 23 milligrams of water, and silicon is recovered as 0.155 grams of silicon oxide. What is the simplest formula of this compound? Okay, now although this isn't kind of what you think of as your classic combustion problem, kind of think about how it's worded. Okay, you're told that you have 0.3 grams of an unknown sample. Okay, so we're given mass of our unknown sample, and it says Mg is recovered as 0.104 grams magnesium oxide. Well, that's kind of similar to how in a combustion reaction, my carbon from my unknown compound is recovered as CO2, right? All it's saying is that the magnesium in your unknown compound is later found in the form of magnesium oxide, right? Hydrogen is found in the form of water, and silicon in the form of silicon oxide. So although, again, this isn't a typical combustion problem, they're really asking you to do the same thing, okay? And so kind of watch for those trends on exams. Sometimes they might not tell you kind of how you're used to seeing this information presented to you. It's slightly different, but realize the parallels between questions that you've seen before. So the first step that I do is I kind of write my equation at the top, right? I have Mg, Si, H, and O, and I don't know the subscripts in any of them. But below it, I wrote my mass of that compound, right? It weighs 0.301 grams. And this gets converted to magnesium oxide, water, and silicon oxide. And I wrote their respective masses underneath. Now, when I laid out the steps, this box indicates kind of your first real step. So again, in this problem, instead of going and solving for how much carbon we have in CO2, we're going to solve for how much magnesium we have in magnesium oxide. Okay, so it's kind of it's just an analogous problem. So if we have 0.104 grams magnesium oxide, we're going to multiply that by 1 mole over its molar mass, which was 40.31 grams is its molar mass. And then there's 1 mole of magnesium per 1 mole of magnesium oxide. We multiply it by just the molar mass of just magnesium. And what we find is that there's 0.0627 grams of magnesium. Now, that means that at the end of the reaction, that there's 0.0627 grams magnesium in magnesium oxide, and that before the reaction occurred, all of that magnesium was in our unknown compound, okay? Now we do the same for hydrogen and silicon, okay? So if we have 0.0231 grams of water, right, we convert that to moles of water by dividing it by its molar mass, which is 18 grams per mole. Now, 1 mole of water has 2 moles of hydrogen. People often forget that little step, right? You have to remember that there's 2 moles of hydrogen per 1 mole of water, and that 1 mole of hydrogen is 1.008 grams, and that we have 0.00258 grams of hydrogen. Now, one question you might have is, how did I know that there was 0.0231 grams of water? Because if you remember, in the problem, it was actually presented as milligrams. And so I first converted 23.1 milligrams to grams, which 23 milligrams is 0.023 grams water, okay? And then again, we do the same exact thing with the silicon oxide, so 0.155 grams of silicon oxide. We convert that to moles of silicon oxide, then to moles of just silicon, convert that to grams of silicon, and what we find is that we have 0.0725 grams of silicon in our unknown compound. Okay. Now the second step, which is the same as, again, the combustion reactions, was to solve for the mass of oxygen by taking the mass of our overall compound, right, which was 0.301 grams, and subtracting the mass of each element that we just found, right? So again, 0.301 grams represents the mass of magnesium, silicon, hydrogen, and oxygen in the original compound. And so now that we previously just found how many grams of each magnesium, hydrogen, and silicon we have, we can subtract to find how many grams of oxygen we have. Okay, so 0.3 grams minus the 0.06 grams of magnesium plus 0.00258 grams of hydrogen plus 0.0725 grams of silicon, and again, those are all in parentheses because we're subtracting all of those, tells us that we have 0.163 grams of oxygen in that unknown compound. Okay, and the last step, last but not least, this last portion that I do is the classic conversion that we do for an empirical formula question, right? So I write all my masses of each element. So 0.0627 grams magnesium, 0.00258 grams hydrogen, 0.07 grams of silicon, and 0.163 grams of oxygen, right? Once I have all of those in terms of grams, I'm going to convert them to moles, which you can see, and then I divide them all by the least number of moles. Okay, so I divide them all by the least number of moles was hydrogen, and it was only 0.00256 moles. So I divide all of them by 0.00256, and that gives me my ratio, which is 1 magnesium to 1 hydrogen to 1 silicon to 4 oxygen. And sometimes when you kind of get these numbers at the end, they'll be off by 0.01, 0.02, 0.03. That's okay. If it's super close to a whole number, it is probably just due to rounding. Okay, and so that's how I knew it should have been Mg1, H1, Si1, O4. Okay. Are there any questions on that?
For those problems, when do you not round? And how do you know that you don't have to round, but you have to multiply by a number, by a whole number?
Yeah, so on the exams, they'll make it very evident when you have to multiply it by a number. So what I'd say, so if you have to round it, your decimal will be 0.5, which should be multiplied by 2, 0.33, which should be multiplied by 3, 0.25, which should be multiplied by 4. It doesn't really get more complicated than that. They wouldn't have the ratio be like 1.13 to 1. That's very hard. You should be able to look at the decimal point and right away know what number you have to multiply it by. And what I'd say in terms of when you should round it, if it's within like 0.05, you definitely should round it. But again, they're going to give you problems in which it's obvious. Okay, so for example, when I solved for the ratio for oxygen, it came out to 3.98. That's so close to 4 that you would just assume that that is 4. Again, if it's something that they want you to round, it's going to end in like 0.25, 0.5, something like that. Any other questions? Okay, so I'm just gonna kind of slowly go through the challenge problems. Again, take a picture if you like them. If not, I actually do have a meeting right after this, so the video will be uploaded still tonight, but a little bit later tonight. And so this is just for you guys to do the first 3 problems. So you have to balance a chemical equation, and you're given 3 reactants, each with their own starting amount. Okay, and so if you want a picture of this, again, probably take in the next couple seconds. But again, it will be posted if you want to reference it later. Okay, and your first 2 questions are very, very common. So the first one is, which is your limiting reactant? And your second one is how much ammonia was produced, which ammonia is one of your products. And again, if you want a picture of this, just in the next 10 seconds or so, because I'm going to go to the next slide. But again, I'm also happy to go back if you need. Okay, 3, 2, 1. This is a little bonus. Because there's 3 reactants, there's actually going to be 2 that are not limiting. And so how much excess is there of each of those? Okay, you can't really put those in terms of a multiple choice because I'd have to say what reactants aren't limiting, which I didn't want to do, but that's good practice. I will also go over that on Wednesday as well, the solution to this bonus question. Okay, but the third question kind of really associated with that equation is a percent yield question. It has a bit of a twist to it. Might be harder than they give you on an exam, might be the same as they'd give you on an exam, I'm not sure. Again, part of what I try to do, because we can't predict what they are going to ask you on the exam, how they're going to ask things on the exam, I try to just make some problems that are looking at topics from a little bit of a different perspective, a different angle, just to, again, make it a little bit more challenging. If I ask them all in the same way every time, it's going to get pretty repetitive, pretty boring. It might also make you think that you know a topic really well, and if they throw you a curveball, maybe not. So again, sometimes I have weird questions, I'm trying to diversify how I ask them. Okay, just another couple seconds on this one. But that is a percent yield question again. Okay, number 4 and 5. Again, chapter 3 is typically a very heavy, long answer chapter. So I made all of these to make all of multiple choice questions. These ones were pretty tough, just because, again, they're very easy to make long answer for chapter 3, but multiple choice a little harder. And so number 4 is a percent yield reaction. It is actually numbers straight out of my lab notebook from research with Dr. Homan. This is actually a reaction we carry out. These really were my masses for my empty vial with my product. And so, yeah, that's kind of just a little bit more of a real life application. You actually could be doing this in research lab or in your job eventually. And then number 5 is kind of theoretically looking at percent yield. So kind of more of a true false, ABC, AB type thing. Okay. And then the last 2 questions are here. So number 7 is, again, a kind of unique perspective on a limiting reactant problem. I've never really seen them ask questions in this way before, but it is a valid thing to ask. You all have the ability to answer that question. But again, it's kind of an atypical way to ask for a limiting reactant problem. Number 6 is your straight up definition combustion reaction problem. So if you've been struggling with combustion reactions or want to see, because I kind of went over a non-traditional one, if you want to see a traditional one, number 6 is kind of your go-to problem. Okay. Okay. Are there any questions here? I'm actually going to stop the recording, but if anybody has questions, I'm happy to answer them.